This is the last couple of pages of your homework. So if you have no idea where I am, I'm on page 9. So this graph looks really confusing, but let's just break it down to what we know. So we have reactants and products. So this is what's going into a reaction, and this is what we're going to get afterwards. So A is energy, and this is the amount of energy in the reactants, and then look at our products. So we have to put a little energy in, and then we must give off energy, because if you put the energy in and it held it, this line would be way up here. It'd be way, way up here, okay? So, and it's not. So here we go. Now, B is without an enzyme. Like I said, when you get grass stains on your pants, you could rinse them, and after hours and hours and hours, you're going to get the grass stains out. Or you could add a little shout or something like that, and it comes out because you're adding an enzyme. So this then is what happens when you add an enzyme. We have to put in way less energy. So this is without the enzyme. We have to put in so much energy, but with the enzyme, it's just really not that much energy. So C then is activation energy with enzyme. There we go. And then D is activation energy, so activation energy without enzyme. Energy without the enzyme. All right, and then E is the amount of energy given off by the reaction. So what is happening at letter B? That is a reaction without an enzyme. What is the relationship between the energy of the reactants and the energy of the products? There is less energy in the products than there were in the reaction. So it was used somehow or given off. Define activation energy. Energy to start a reaction. RXN means reaction. All right. Which letter represents the activation energy for the reaction? Without enzymes. So that is going to be this whole amount right here. So that's letter D. And then with enzyme, it's a lot less. So we know that that's that one right there. So that is C. What does letter E represent? That energy is given off, that it is exothermic. It's giving off energy. Okay. So what is the role of enzymes in biological systems? Without enzymes, life would cease to exist because it would take too long for any reactions to happen without an enzyme. So enzyme specificity, oh my goodness, I heard all sorts of people looking this up, and they were quoting from Google or Wikipedia or whatever. Specific enzymes. So I think we drew it in your notes. Remember, we drew something like that, and then we had a substrate that we were breaking down. So if this is the substrate, the orange one, this enzyme only can act on things that are this shape. So if something came in and looked like this, it's not going to break that down. So it matches by shape. All right, I'm going to let you answer those. All right, so now this is part of the notes as well. So what happens when the rate of an enzyme-controlled action when the substrate level is high and remains high? So here's really, if I have to sketch this out. Okay, so let's say we've got a graph, and this is our rate of reaction, rate. Okay, and this is over time. We'll go time here. Okay, so it says what happens when the substrate level. So we're trying to break down starch, like the spit in the beakers that I had. So it was slow at first, and then it went up, and then it broke things down really fast. So what happens is it's going to level off when the substrate level is high, because you only have so many enzymes. So if I set out one stapler and I had all 70 of my students trying to staple their papers, you can only go as fast as the one stapler. You can't, just because there's 70 of you doesn't mean all 70 of you can staple your paper at the same time. And why does this happen? Because it levels off, because the word is, it is saturated. Now, if I had 70 of you and 70 staplers, we're going to get done really fast, because not all the enzymes will be saturated. Not all the staplers will be being used because you have your own. All right, I think this makes sense. Our body temperature is 37 degrees, 37.1. So both of these could work a little bit in the human body, but not great. J works really good at about 50. That's way hotter than a human body can be. Now, I really like this one. Okay, and a question that I would and could and will ask you is like, can K and L exist in the body together? Well, they don't even work in similar environments. K works at 2, L is working about 9. That's not even the same environment. So they could both be in the human body, but not in the same organ. So this would be like, K would be your stomach, and then L would be like your duodenum, which is the beginning of your small intestine. And that's actually next week's lesson. Okay, what happens to the enzyme activity when the pH is lower than the optimal pH? It quits working. So it works a little bit, but it's not great. So it is going to work a little bit, but it's not going to work at its optimum temperature. And I'm not too worried about these, other than you should know that vitamins are coenzymes, okay? And it's chemicals that inhibit enzyme activity. Those are inhibitors. And it could be competitive or non-competitive inhibitors. I'm not going to really ask too much about this, so I am going to tell you right now. These two are the ones that you're going to have to know. I'm not that worried that you get these. I really like this picture right here. This is competitive and non-competitive. So here's the active site. I have it in orange right there. So B should match at that active site. But in this case, this guy, C, he competes, that's the word, competes with the active site right there, and B can't get in there. B can't get broken down. So now a non-competitive inhibitor this is the same enzyme, so if you look, it's the same enzyme, but this guy is joining right here. That's a non-competitive spot. So what it does is it pushes the active site out so that B can't get in there. If it can't get in there, it can't get broken down. And then these are awesome, and this is very similar to what your test will be.